Bismillahirrahmanirrahim. In the last session, we discussed the planar dynamical system where the eigenvalues of the corresponding matrix involved were both purely imaginary. But today we will be considering the case where the eigenvalues are complex. In other words, they are having both real and imaginary parts. And in particular, we will be considering a specific kind of system that is given by this way: x prime of t to be a times x, where a is my alpha, beta, minus beta, alpha. So the system should look like, so the system has to look like x prime of t is to be alpha times x plus beta times y, and y prime of t to be minus beta times x plus alpha times y. So we will be discussing this kind of a specific system for now, and we will analyze it, uh, how what are the eigenvalues, and what are going to be the solutions to this kind of dynamical system, and then we finally be moving towards the phase portrait. In other words, we will be looking at the solution trajectories. How do they behave? So let's first find the eigenvalues. So let's calculate eigenvalues. Okay, so my matrix A is given by alpha, beta, minus beta, alpha. And for the eigenvalue, we all know that we need to calculate determinant of a minus lambda time I and have to set it to 0. In other words, we have to find the determinant of alpha minus lambda, beta minus beta, and alpha minus lambda to be 0. That gives me alpha minus lambda squared plus beta squared to be 0. That again gives me alpha minus lambda squared to be minus beta squared. And it's not hard to show that this gives me alpha minus lambda to be plus minus iota beta. That shows that my lambda is going to be alpha plus minus iota beta. So the eigenvalues are going to be lambda 1, let's say alpha plus I beta, and lambda 2 is alpha minus I beta. So in this case, now we will be moving towards finding out the eigenvectors, but I'll suggest that don't go for both, just find out the eigenvector corresponding to any one of these, and I'll be going with this lambda 1. So lambda 1 is alpha plus iota beta, and I'm interested in the eigenvector for corresponding to this eigenvalue. So for finding out the eigenvectors, all we need to do is we need to find solution to this system, that is 0 column vector, and a is, we know what is our a. So a was alpha beta minus beta alpha, and then you have to subtract from it alpha plus I beta 0 0 alpha plus I beta, and all of this thing has to be applied on xy this vector, and it has to be set equal to 0 0 column vector. And this again gives me, after some algebraic manipulation, it gives me minus I beta beta, and then minus beta, and then I beta minus I beta applied onto xy to be 0 0, which implies minus I beta x plus beta y to be 0, and minus beta x minus I beta y to be equal to 0. It's not hard to realize that this equation 2 is multiple of the equation 1. That is, you just multiply this equation 1 with minus iota and you will get the equation second. So from both of these equations, it's basically one equation, loosely speaking. So sorry, we get y to be I times x. So if we set x to be t, then y has to be it. Or the eigenvector has to be t comma it, that is t times 1I. So the eigenvector should be 1 and I. So this is going to be the end result. Lambda 1 is alpha plus I beta, and the v1, that is eigenvector, is 1 and I. So solution should look like x of t to be equal to e to the alpha plus I beta applied to t multiplied with 1I. And then again, as usual, we open up this thing with Euler formula for but before that we can simplify it a bit more. We can write it e to the alpha t multiplied by e to the iota beta t, and then 1I. Okay, now I can open it with the help of Euler formula, and that gives me cos beta t plus I sine beta t, and multiplied with the vector 1I. And then you can again simplify it a bit more to write it like e to the alpha t cos beta t plus uh, iota times e to the alpha t sine beta t, and then minus e to the alpha t sine beta t plus I e to the alpha t cos beta t. This is just algebraic manipulation of complex numbers. You can easily sort it out. So what we get from here, further we can simplify it a bit more to write it in the form that looks like this. X of t is e to the alpha t multiplied with cos beta t minus e to the alpha t multiplied with sine beta t, that is sine beta t, plus iota times e to the alpha t, and we have sine beta t, and e to the alpha t multiplied with cos beta t. So if we label as we did last time, this one is the real part and this one is the imaginary part of the solution, then it's not hard to show that both of these are the solutions like we did last time. Both of these are the solutions to the main system, and hence their linear combination. uh, why do we consider these two parts as our solutions? because when we will consider this solution x of t to be c1 times this real part plus c2 times this imaginary part, then we are kind of away from the complex numbers. So we have got rid of the complex number. Now this is the solution, general solution, and uh, which is free from the complex numbers, and it's basically good. Why? Because the original differential equation is also in the real form. I involves real numbers, so like this is something nice to have it. So we have this one as a solution. So the solution has to be this x of t to be equal to c1 times, like you can put just these values and you can write it c1 times e to the alpha t cos beta t plus c2 times e to the alpha t sine beta t, and then you have minus c1 times e to the alpha t sine beta t plus c2 times e to the alpha t cos beta t. So this is going to be a really the general solution to our system that we had in our hands. Or we can write the solution as x of t to be equal to c1 e to the alpha t times this cos beta t minus sine beta t plus c2 times e to the alpha t times sine beta t and cos beta t. Now, in the previous example where we were considering the eigenvalues as only purely imaginary, we did not have this term. Okay, we did not have this term. We were having only this term and this vector and this vector, column vectors. And in that case, we realized that the phase portrait were circles centered at origin, centered at origin. Okay, when e to the alpha t was absent, like it wasn't present over here. But with the involvement of this term, like when this term gets involved, this x of t, which were previously kind of circles centered at origin, now these are going to be spirals. So either they will be uh, directed towards or moving towards origin. In other words, you know spiral sink you can call, or they are going to be directed away from origin. Okay, in other words, it will going to be a spiral source. So now the question will be, when this solution is going to be spiral sink and when it is going to be is showing a spiral source. In fact, we will not call this solution as a spiral sink or a spiral source, but the fixed point, that is origin, will become either a spiral sink or a spiral source. When the trajectories will be moving towards it, it will, the fixed point 0 0 will be the spiral sink, otherwise it will be spiral source, and that will be elaborated in the next coming video.